Hi everyone. As Dr. Chin and Dr. Hazan has said before, I'm Serena Hollis, and I'll be presenting my project that I've been doing for the past couple of months involving making a numerical model to predict potential COVID-19 cases for the upcoming fall. So before I start, I just wanted to tell you a little bit about myself. Obviously, I'm a participant at the RU at the University of Tennessee, Chattanooga. But like I mentioned before, I'm also a student at Ashland University, where I'm an undergraduate, where I'm studying biology as my major, computer science, and psychology as my minor. So as everybody is obviously aware, we're in a new pandemic involving coronavirus as SARS-CoV-2. And since it's a new strain of virus, it's been able to spread very quickly and rapidly across the globe. And since it's been spreading very quickly, we are currently in a pandemic for a foreseeable future. So knowing the possible amount of cases that are going to be happening in the future is very beneficial to know, so that companies and the government can implement new policies regarding mask use, social distancing, stuff like that for public safety. And right now, this is basically the amount of global cases that we have as of about a week ago. So as you can see on the map, the smaller dots mean there are smaller cases of COVID-19. The larger dots mean there's more cases, up to about 40,000, but I think in the US it may be more. And the higher cases are most likely due to higher population density within a small area. So like I mentioned before, some of the largest amounts of cases are in Brazil, India, US, Iran, and South Africa. The highest range of this is about 30,000 to 40,000, and in the US alone, New York has about 20,000 of these cases. But the smallest amount of cases have been seen in the rural US, mostly in the northwestern regions, as well as Japan, Iceland, and Denmark, where their cases are about in the single-digit range. And some countries even have about no cases at all, which is very nice. So you may be wondering why we wanted to use climate variables. So in the beginning, it was unclear if climate actually played a role in the spread of the virus. So we wanted to explore that if the rate of new cases would increase or decrease with time as the weather changed over the seasons. And again, this relationship between the climate and COVID-19 was an open resource question, so no one was particularly looking at it before. And ultimately, our goal was to provide a numerical model to predict COVID-19 cases for the future using GIS with climate and population variables as its factors. So we have three main objectives. The first one was data acquisition and processing. Basically, I was collecting data from Johns Hopkins and a website called Copernicus, which is basically a weather storage data facility or data website which supplies weather data from the past couple of months as my data for the project, and making sure that it's being assigned to the right longitude and latitude, as well as the right county and the right date. And then I would use that data to provide a regression, which would then provide with me an equation in a GIS environment using my climate variables and population density. And then from there, with my equation, I would generate more maps to show the potential spread of COVID-19 in the fall. So I mostly used 4 data types. I used air temperature, which is just what we think of regular temperature. Soil moisture, which is related to precipitation. So if a particular season was more dry or more wet. And then soil temperature, which is similar to air temperature, but it's not as volatile. It's not easy to change. And then population density, which is, again, just the number of people in a certain area. And then the 3 data collections for the weather were collected on a weekly basis based on Mondays at 5 p.m. I chose Mondays at 5 because I figured that would be a good time where people would be more active outside, whether they were going shopping, going out to eat, coming home from work, stuff like that. They'd be more active outside. And then for the training of the model, I used data from January when the first case of COVID-19 appeared in the US, all the way up to July. And then for my predictions, as I said, they were going to be used in the fall. So I used previous weather predictions from our previous weather data from last year for August through October, with the assumption that the weather for this fall is going to be about the same for this upcoming fall. And then the weather data was also in a grid format, which basically means that the data is continuous, meaning that it sort of blends together. It's not like in little chunks of different data. And then as far as my study sites, I tried to make sure that I had study sites that were all over the US, gaining me a total of 20 counties so far. And all of these counties ranged from about high cases to medium cases to low number of cases, so that it could increase variability within my study. And then for the actual production or my methods, I first used linear and nonlinear regressions to test an equation that would produce my predictions. And then I figured out that the best method for my predictions would be to use a linear regression. I also tried ordinary least square and geographically weighted regression, but they were producing poor quality results, so I couldn't really use them. And then all the methods that I used use a spreadsheet that I have of all of my weather data spanning from January to about July. And this is just an example of my spreadsheets. As you can see, they're all separated by date, and then they have the county and the county name, as well as the confirmed cases, which is the variable that I used for my predictions. So as you can see, like I said before, a lot of them have cases up in the tens of thousands. Some of them have 0, some have single digits, some of them are only about 100 or so. And then at the end, you can see that I also have my weather data as well as my population density data. So in order to create my prediction equation, I used a program called JMP, which is basically a statistics program. And then from there, I entered in my variables as well as my confirmed cases into a fit model analysis, which basically basically visualizes how the Y, which is my confirmed data, with the X, which is my 4 variables, as you can see on the screen, and see how well they fit together, as well as generating a prediction equation so that I could produce basically what things would be similar results. So from here, you can actually see which variables would affect the prediction model the most. And on the bottom, you can see that it has P equals, which is basically the amount of leverage that that variable has, and the lower the P value, the higher the leverage that it has. So obviously, population density is going to have a big effect on how many COVID cases there are, but temperature also had a big effect on the number of cases as well. And from there, JMP also gave me my equation data, or my prediction equation, which is this, and I'll explain it just a little bit. So ST would be my soil temperature, T would be my air temperature, SM is my soil moisture, and then PD is my population density. So basically what I did for each of my predictions, I just entered in the same factors into this equation, and then it spit out a number for me. JMP also gave me my R squared and my R square adjusted, which basically tells me what amount of confidence that the program has that it's accurate. So it gave me about 60%, which isn't too bad. And then for my prediction data sets, I prepared them the same way as I did with my training data sets. I got weather data from last year because, again, we're assuming that the weather last year is going to be the same as this year. And then I affixed them to the right spots for all of the United States, not just the 20 counties, as well as its population data. And then for the predicted cases, I put in a new field in GIS, and I used that equation that I showed you before to combine all of those different data sets factors into creating a new predicted case column for me. And then for dates that have already passed, because I wanted to validify my equation, I also made a residual column, which calculates the difference between the confirmed cases and the predicted cases. And then just add a summary. a prediction model was made using linear regression to make a linear equation. I used that equation to predict dates or to predict cases for already known dates. And then as I was training the model more and more, I added more dates to accommodate variance. And then the final equation was used to predict cases for the upcoming fall. For my results, as I mentioned before, JMP told me that the two factors that played the most in the equation was population density and then air temperature. And so from there, I was able to produce five maps that show the residual for validity, and they span from about May to July 2020. And then 5 maps were also produced to predict the future cases for August through October. So what we're looking at right now is one of my residual maps. Basically the green range to about light yellow or light orange shows cases where my prediction was too high, and then from dark orange to red is where my predictions were too low. And right now, as you can see on the bottom, it gave me, I have a margin about 500 where my prediction was actually pretty close. And the smallest margin was about 180 for, I believe, June 10th. And again, a lot of my predictions were mostly on the too high side or too low side. None of them were like very close. But again, as a prediction model, it's not always going to be super accurate. And then, like I said, for June 10th, my closest margin was about 181, which is, again, pretty nice for a prediction model, especially one that I've first created for the first time. And then for my actual predictions, I just wanted to remind everybody that I use an equation in JMP to produce the predictions, and then I actually map them out in GIS. And these maps showed the predicted number of cases as well as the severity. So in end of August, we have this map. Obviously, the numbers are probably not going to be correct, but I think if you look at these maps more as what the severity is going to be for the future months, I think it shows more accurately. So places that are like very crowded with high population, like Southern California, Texas, Florida, the East Coast, most big Midwestern cities like Cleveland, Chicago, Cincinnati, places like those, they're going to have a much higher much higher number of case numbers. And I think my maps for the October show this the best. And as I said before, a lot of places with a high density number are going to show higher numbers. And again, like I said before, a lot of these places with a high population are going to have high numbers. Southern California, a lot of the southern states, a lot of the East Coast, while a lot of the rural areas like Northwestern, some of the Midwest are going to have a lot of lower numbers. And again, same thing. So as a conclusion, with the current trend of COVID-19 cases, obviously they're going to be rising with the upcoming of fall, especially in areas that are so highly populated. In areas that aren't as populated or less dense in people are still going to be effective, but not at the same rate as these higher density areas. And for the model, it's hard to predict for these areas due to their variability within each county. And then I think mostly my prediction model is probably more effective for these highly populated areas more than the lower populated areas. And then a few challenges that I faced during this research was mostly the collection and consistency of the raw data. As I mentioned before, I got a lot of the COVID-19 data from Johns Hopkins, and especially the early data. It's not as organized or not organized in the same way as it is now, because again, COVID-19 hit the US very fast. So a lot of the data is not very consistent. So a lot of the project was me trying to wrangle the data, making sure it's all formatted in a consistent way to make sure that all my data is arranged and assigned the right data correctly. Another challenge was testing and building the actual prediction model and making sure it's somewhat accurate and not just giving me crazy results, which is just a challenge that comes with the territory. And then assuring all of my data was assigned correctly and didn't result in unexpected null data was also one of the struggles, which goes again with the consistency of the data that I actually got, which made it kind of a trouble. I know there was some places that were assigned as the US that weren't actually as the US. I think one example is the Diamond Princess, which is a cruise ship that was, I think, near the Caribbean or the Bahamas during the beginning of the year, as well as some states or some counties being counted as 1 or 0 inside of the data sheets that I got from Johns Hopkins, which I can understand since it was probably very difficult to get accurate amount of numbers with so many people getting tested at especially the beginning. And then some improvements that I would make overall would just be to make a smaller scale version of this prediction model, particularly one that might do individual states like Ohio, since I'm from Ohio, or Tennessee, since this project was based in Tennessee with the university or UTC. And instead of doing it by county, I would do it by city, since that would increase the variability for my prediction model. Then I would also focus more on the effects that seem to affect the model much more, like population and air temperature. And then I would also consider new variables like social distancing, mask use, the opening of public areas like restaurants, stores, public spaces, anything like parks, stuff like that. And then for any future research, I would probably compare the case number progression to other countries, see if we're getting more cases per day than other countries or less cases per day than other countries. I would also compare the confirmed case through death ratio from the beginning of COVID-19 maybe towards the end. See if more people were dying towards the beginning or towards now or towards like maybe a couple of months from now, and see if maybe treatment has gotten better for them. And then I would also compare the case rate number progression from now to about maybe 6 to 12 months from now. And better at slowing down the rate at which people are getting sick, and maybe even compare the numbers to when a vaccine is widely released. And then finally, I would just like to thank everybody at NSF and the REU and at University of Tennessee, Chattanooga. I'd also like to thank Dr. Quinn and his lab, as well as Dr. Hossein for being my mentor all year long. It was great working with you. I'd also like to thank everybody that came here for my invitation. It was nice to see you all here. And then for references, as I mentioned before, I mostly use Copernicus and Johns Hopkins for a lot of my weather and coronavirus data. And then I would just like to open it up for questions.
Questions?
Good job, Serena. This is Dolly.
Dolly.
Yeah, I'll turn on my camera, I guess, so you can. So good job on that. Actually, one of the questions I was going to ask you was about the effect of spatial scale in your analysis. I'm sure you're well aware, probably more than I am, that the spatial scale effect is bound to be pretty significant in your study. So I definitely agree with you. I think it's a worthwhile endeavor to kind of subdivide your model into different spatial scale buckets and actually compare the sort of regression effects that you get at each scale. One of the things I wanted to ask you was if you considered doing any kind of ensemble forecasting or ensemble modeling where you combine multiple models to actually come up with sort of a consensus model to actually base your predictions on. Have you done anything like that?
Actually, no, I haven't considered that. Basically, this project was me more of sort of learning to use GIS a lot better to make prediction models, since, again, I mentioned this is my first time doing something like this, especially with prediction models.
No, I think it's definitely robust. I admit I've not used JMT all that much, so I was really impressed that you actually developed your training and testing model inside GMT. That's actually really cool. Other quick question I have, I don't want to occupy too much time so other people can jump in. Are you anticipating or assuming that the relationship with population density is a kind of a indirect effect or an indirect measure of human activities? So the idea that humans are going to be more active in certain ranges of temperature than they would be in others, is that the idea?
I think so, but also just as a general, we were looking at weather first with COVID-19, but then we also considered population density. So it wasn't like one is affecting the other, but we were also assuming, since people were thinking, oh, with summer, cases are probably going to go down, but obviously they went up as people are going to be out more and more despite regulation or recommendations.
Right, right. So yeah, it'll be interesting to see. I do also agree that with your assessment that maybe a more limited a model with more limited numbers of independent factors would actually be really useful as well to kind of remove some of the statistical noise in your model. You actually might see better R-squared values, for example. But yeah, nicely done, Serena. I'm really impressed with the work that you've done. And I also want to reach out and make note of the work that you've done with both Dr. Quinn and Dr. Hussein. I'm glad that they were able to work with you. You've actually come a long way, so good job.
Thank you.
Thank you.
Thank you. Can I ask, this is Ms. Dolly Crawford. Are you Serena's formal advisor or?
No, Serena was actually in my GIS class this past semester. So she's got a very strong background, as you know by now, I'm sure very well, a very strong background in computational biology, but also computer science. I think she's definitely got the intellectual and academic foundation that she needs to develop more robust spatial modeling endeavors, much like the one that she's been working on with you. So yeah, I know her from biology generally. She's obviously a student in our program at Ashland University, but I know her a little bit better because as a result of her being in the GIS class.
Yeah, I would like to attest to that. And the first thing I gave Serena at the beginning, an exercise that was actually used in my upper level GIS class. And I had graduate student in that class. I literally gave, that was the first exercise that she did. And I provided instructions, and I was really impressed to see that she didn't ask me any questions. She completed the exercise. That, inspires me. And JMP is a very complex statistical software. I just told her you can download it for 1 month and then for free. Then if we need more, then we'll pay. And she literally figured out that everything by herself. So that was pretty impressive, I think. And I told her that so for all RU students, I think we need to make effort to reach out to mentors and see that we can produce something publishable. I think it's a great effort from NSF, and the way I can see that the students and getting interested in their research. I think that was the purpose. I think, and
I definitely see how this could easily be published. So it's definitely a good model. It's a good start, Serena. I definitely encourage you to continue working on that.
Yeah, one thing I like to also add that regarding to your question, looking into different models, and I think the time period, the data that she handled, she piled up. I think it's the compilation of the data itself is a great contribution for to start this pandemic. And we're going to have those data set in the cloud, so all the climate variables for those 20 counties and for the month of January to July for every week. So that spreadsheet can be used for many different types of modeling. So I think that is something that we have planned to do something in the future, I think.
That sounds wonderful. It'd also be interesting to see how well her model matches up with some of the broader forecasts that are being made, for example, by the University of Washington.
Exactly.
The problem lot of interesting.
I think the prediction that she got a good R square, and but there's no data to validate what she predicted in fall. Nobody has that. So that's why she validated the model for the weekly data that the cases, those are known. So although I think, it could be better to understand some of the data in the map. Sometimes, the GIS, they provide the range. Maybe the extremity that we have, that's not the case. There are probably some noise. The cleaning, filtering those data, that needs a little bit more time. But I think, I'm sure, she definitely, got the experience of this very, very relevant research and doing at very high end. And GIS gives a perspective to see things in maps that helps to understand well. And this equation is meant to provide one tool to predict for the entire United States. That is very, very challenging. But I think we need to look at that angle too. She could do something for state by state separately, but it's also important to see if we can develop something that gives the overall perspective. I think that was one of the goal of our research.
Yeah, I would even argue that despite the fact that it's obviously very timely and it's a very interesting application of both the regression analysis and the combining that with GIS, I would argue that some of the spatial scale questions are, to me at least, are some of the most important and interesting parts of your work, is to kind of examine how the temporal but also spatial variation in the model and how that changes over space.
Exactly.
It's really useful.
Yeah. She tried the other models, the logistic, geographically weighted regression, ordinary least square regression. Those only work only one date. Yeah. So that around then piling the temporal that gives a lots of variability. And that's how our R-square got improved. Anyways, it's Serena's work, so I think, if anybody has other questions, I think she should, entertain that. So,
Professor Crowell, we also appreciate you sent Serena to our program. Really appreciate that.
I have a question, Serena.
Yes.
Hi. So you said temperature was contributing to your model, your final model?
Yeah, temperature was contributing probably the most, or not the most, second most.
Second most. I was just curious about what that relationship was and whether you think that's a direct impact or maybe a more of an indirect effect, given
now that I think about it, it's probably more of an indirect impact. Since originally we were supposed to be on lockdown over the summer, obviously that didn't stick. So since during the summer people are going to be out more, since it's hot, more people are going to be around others. So that's obviously going to cause an increase in cases.
Yeah. Are the
more better as an indirect effect? Yeah.
The regional progression of sort of the highs and the lows of COVID over the course of your study period, could that affect the way temperature is behaving in the model?
I think so too, since obviously more places are going to be hotter than others. So that might have some indirect effect, but I think in general it would probably work more of the same. But obviously places in the US that have like more extreme temperatures all throughout the year probably won't have as much as an effect, like Alaska or Florida or California. Arizona probably won't have as much of the same effects. But I think that's probably more based on their population.
So was temperature a positive contributor to COVID cases?
I think so, yeah.
Rather than negative?
I think so.
The coefficient of the model, I don't remember what you put up, but
I can go back.
Okay, it's fine. Because it's just confusing to think about. It spiked up in February, March, April, and then it started to go down, and then it went up again when it was getting hot. So if I were just thinking about this off the top of my head, I'm not sure what I would predict for the relationship between temperature.
Yeah, it's hard to predict purely based